Good afternoon. We present to your attention a research on the topic geometric and topological structure of LLM responses under prompt variations. Authors of the work it's Denis Simonov, Alexander Polagin, and Yegor Simonov. Today we are discussing the stability of large language models. While modern LLM produce high-quality text, they suffer from a major issue, prompt sensitivity. Even minor semantic or structural changes to a query can lead to inconsistent logic or content. This makes it very hard to rely on these models for critical tasks. To solve this, our research proposes a new way to measure stability by treating the set of model responses as a geometric and topological structure within an embedding space. The primary goal of this study is to create a formalized model that provides a quantitative analysis of how stable an LLM's response space is when faced with different prompt variations. To achieve this, we have set several objectives. First, to define the response space mathematically. Second, to establish geometric metrics for dispersion. And finally, to use persistent homology to create an integral stability indicator, which we call S-top, to measure how well the model preserves its response logic across variations. To analyze this mathematically, we define the LLM as an operator that maps a query space Q to a response space Y. Each text response is then converted into a high-dimensional vector using an embedding mapping. Instead of looking at a single answer, we analyze a family of responses generated from variations of the same base query. We then measure the distance between these responses in the embedding space to understand how much the model's output drifts when the prompt changes slightly. We distinguish between two types of transformations. First, semantic transformations, which involve changing the wording or using synonyms while keeping the meaning identical. Second, structural transformations, which are more about the layout of the prompt, such as reordering instructions or changing the formatting. Our research assumes that if two queries are equivalent, meaning they ask for the same task, the model responses should ideally remain invariant or stable across both types of changes. To analyze the global structure of the response space, we use persistent homology. We built a sequence of geometric shapes called Vietoris-Reeves complexes. As we increase the scale parameter epsilon, we track two k invariants. Beta 0, which tells us how fragmented the response space is, and beta 1, which detects cycles or loops. By looking at how long these features live during the process, their persistence, we can distinguish true structural properties of the model from local noise or random fluctuations in the embeddings. We introduce a single master metric called S-top, or the integral indicator of topological stability. This formula aggregates three main types of disorganization: fragmentation, noise, and complexity. If the value is close to 1, the response space is coherent and the model is stable. As the value decreases, it signals that the model is becoming disorganized, either because it's splitting into multiple disconnected answers or because it's producing a complex, inconsistent structure of responses. To get a more detailed view, we break down the stability into three partial indices. The component stability index measures how in one piece the answers are. The complexity index shows if the model is oscillating between different generation models. Finally, the sensitivity index is crucial. It directly compares how the model reacts to simple wording changes versus changes in the actual structure of the prompt. Together, these allow us to diagnose exactly why a model might be failing a stability test. Based on these metrics, we classify LLM behavior into three models. In a stable regime, the model is invariant. It gives the same core answer regardless of the prompt's form. In a moderately sensitive regime, we start to see some dependence on the formulation. However, the topologically unstable regime, we see a total breakdown. The response space splits, meaning that slightly different prompts activate completely different and often inconsistent generated models. This topology helps us identify when a model behavior becomes unreliable. We begin by comparing how the model's generation mode affects its response space. In the deterministic mode, where the temperature is near zero, the responses are highly consistent and form a compact cluster with very low pairwise distances. However, when we introduce stochasticity through temperature sampling, the variability increases significantly. While the space remains globally connected, we see a dramatic decrease in the stability indicator, meaning the responses become much more geometrically dispersed. Next, we looked at semantic variations, basically asking the same thing in different words. Factual queries are the most robust. The model's answers stay very similar regardless of phrasing. In contrast, logical and instructive tasks show much higher sensitivity. Interestingly, while the distance between responses grows, the global topological integrity remains intact, meaning the model isn't yet breaking into a completely disconnected response cluster. When we move from semantic paraphrasing to structural modifications like changing the format of the instruction, the impact is more pronounced. This is especially true for complex cognitive tasks. We observe a gradual fragmentation of the embedding space, evidenced by the increasing number of stable connectivity components. Essentially, structural changes force the modeling to move more diverse and less connected regions of its response space. Comparing the two types of perturbations directly, it's clear that the model's internal logic is more sensitive to how an instruction is structured than to the specific words used. Our statistical summary shows that while factual queries remain relatively grounded, logical queries experience the most significant drop in the topological stability when the prompt structure is altered. This highlights a potential vulnerability in how LLMs process complex reasoning tasks. In conclusion, our research demonstrates that we can quantitatively map the behavioral space of an LLM. We have shown that while models are fairly resilient to simple paraphrasing, structural changes in prompts can lead to significant fragmentation of their response logic. This framework of topological stability gives us a new tool to identify when a model is at risk of becoming inconsistent, helping us build more reliable AI systems. Thank you for your attention.